What's up guys, this is Jahangir from Medporium, and today we're going to be getting into some real organic chemistry. Now today's a Friday for me. I don't know when this video might be uploaded, but I'm in a good mood. I'm ready to get into this stuff. So first off, we have to talk about different configurations or projections, I guess you could say, of how to look at these organic molecules, because most of them are going to have like this 3D arrangement, and we're not going to be able to show that on a 2D piece of paper. So we need to do our best to do that. So there's two ways in doing that. First is the sawhorse, so I guess we could call it sawhorse projection, and then the next one is called the Newman projection. So Newman projection. All right. So the difference between the sawhorse and the Newman projection. So sawhorse is going to be, it's going to look like your generic organic molecule, the 3D organic molecule that we're going to try to draw it out as a 2D model. So it'll be something like we have a carbon over here, we have hydrogen, and a hydrogen over here, then that's bonded to a carbon. This is going to be hydrogen, yet another hydrogen. So this is what we might see in like a sawhorse projection. And this is how we're trying to distill a organic molecule into what we might see from a 2D dimension. So this is another way of writing this out is I'm going to color code this real quick. And let's just say carbon is blue. So we're going to have, let's say we have two of these blue dots, so that's one dot over here, two dot over here. Hopefully that's big enough. And let's say our bondage is with this gray, so there's a bond right there. Then we're going to have three carbons, and carbons will be red. So I'll just do just a little dot right there, since hydrogen, or I think I said carbon, hydrogen is much smaller than carbon. So we have those hydrogens right there, and this, it's not a good image. I know I'm not really good at drawing, but this is what our organic molecule is going to look like. And if you want to draw as like a rough sketch, like just drawing it colorfully, but this is what the sawhorse projection looks like. Now we're not going to really be looking at the sawhorse projection because we have a superior model to look at, which is the Newman projection. So Newman projection is, we're looking at, let's say we're looking at this middle of a carbon right there. So we're pretty much taking our organic molecule right here and moving it so the carbons are aligned at the same position. And what that's going to look like is we have this circle over here, and this circle is going to represent our back carbon. And I'm going to have a decent sized dot right here. And that is our front carbon. So I'm going to label this real quick. So over here, this is, let me do a smaller font to label that. This is going to be our back carbon. So I'll just do back C. And this dot over here will be our front C. So hopefully you can write that down, because I'm going to erase it and write out some of our hydrogens real quick. So let me erase this over here. And now let's bring in our hydrogens. So if we're looking at this sawhorse projection over here, if we're twisting it and looking at how the carbons are aligned, then we're going to have a hydrogen sticking up here, over here, and down here in our front carbon. Then we have to account for our back carbon as well. So that's a hydrogen right there. We have another hydrogen, and we have another hydrogen. And that is our Newman projection. So Newman projection is when we're basically we're moving our organic molecule, and we're having the carbons aligned and pretty much writing it out, seeing how that would look like. So one thing you have to understand, and this goes out for physics, this goes out for even Gen Chem, is this big concept you have to know, is that the lowest energy is going to be the most stable. So I'll write that down. I'll just do this, low energy. So low energy equals, oh, that was a terrible Y. Let me redo that. Energy equals more stable. So what I mean by this of having low energy is more stable is we're going to be talking about different strains here. We're going to talk about torsional strain. We're going to talk about steric strain, and we're also going to talk about angle strain in our next videos. But if we have less energy between these atoms, if they're not repelling each other, because when we repel, if let's say these hydrogens weren't getting along with each other, there would be a repulsion force, and that's where we get energy from. And if we have less of that, we have a more stable organic molecule. Now, if we have more energy, so more energy, let me write that arrow better. So more energy, this is going to be less stable. So less stable. Now, like we were talking about with our different strains, one thing to actually note is that if we have lower energy, we're going to have this configuration called the staggered. Staggered. So we have staggered configuration. And staggered configuration is going to be when all of those CH bonds are farthest apart. So if they're farthest apart, they're not going to repulse each other, and we have less energy. So there's not going to be a lot of drama between those atoms because they're farthest away from each other. So our Newman projection over here is a staggered conformation or staggered projection because those CH bonds are farthest away from each other. Like as you can see, this is the farthest that they can get away from each other while still being bonded to each other. So this is going to be our staggered, and I'm going to write this over here. I'll just write farthest. So farthest apart. Hopefully you understand that what I mean by farthest apart is those CH bonds being farthest apart. Now, if we have high energy, this is going to be less stable. And this is going to create something called the eclipsed. Oh, shoot, that's wrong. Eclipsed conformation, eclipse formation. And this is going to be when pretty much the opposite of staggered, when they're the closest together. So I'll write this over here. Closest together, and just like before, hopefully you understand that what I mean by closest together is those CH bonds being closest together. So what does an eclipse conformation look like? So we already drew our staggered over here, and just if you're curious, this is ethane. So we have ethane over here because we have two carbons, so we have ethane. And what eclipse is going to look like, let me just copy this so I can scroll down real quick. So this is our staggered, and I'm going to write this in yellow. So this is going to be our staggered. Now, if we want to see what an eclipse looks like, I'm just going to copy this. Well, actually, I already copied it. Here, I'll move this over here and take this Newman stuff out of the way. And let's see. So if we're looking at eclipse, they're going to be the closest together. So instead of this staggered position where they're farthest apart, what this is going to look like is this H over here might be somewhere like that close. Actually, let me redo that. So we're going to have our H right here. And it's going to be as close to the front carbon H as the back carbon H. So those are going to be really close to each other. And I'm going to do the same exact thing for the other ones. So this guy over here is going to be closest to this hydrogen over here. So let me write a better H for that one. And this hydrogen will do the exact same thing. And let's twist that a little. And we're going to have that. And this is going to be eclipsed. So I'll write this over here, eclipsed. So as you can see, those hydrogens are as close together as they can be. And this results in high energy because those hydrogens don't want to be as close to each other as possible. It's creating this repulsive force that results in higher energy and makes this less stable. And this is going to result in 12 kilojoules per mole of energy. actually rewrite that. Man, my handwriting is terrible. But this is going to be 12 kilojoules per mole of energy, because each of this hydrogen over here, this energy over here is 4. This one is 4. This one is 4. 4 times 3 is going to be 12. And that is what is known as torsional strain. So I'm going to pull up a different color over here, and I'll write this somewhere down here. Let's do this. Torsional. So torsional strain. So what is torsional strain? Well, torsional strain is the repulsion forces between those bonding pairs. It's just the strain created when you're misaligning those bonds, meaning those bonds just don't like each other, and that's the strain that's caused by it. So these are specifically about the bonds. So if we look at our CH bonds over here, there's torsional strain because this CH bond is close to this CH bond over here. Let me actually get my highlighter. So this CH bond is really close to this CH bond over here, and that creates torsional strain of 4 kilojoules per mole. Same story over here. They're really close, and over here they're really close as well. So that is going to be torsional strain, and for those of you guys that want to write this as notes, I'll write it over here. So torsional strain is going to be repulsion. So repulsion between, I'll just do BTW, even though that means by the way. I'll just put, hopefully you understand that BTW in this case means between, sorry. I'll put BTW. Hopefully you understand that in this scenario, BTW doesn't mean by the way, it means between. So repulsion between bonding, oh, that was a terrible B. Bonding pairs. So this is going to be repulsion between bonding pairs. Like we said, our CH over here and our CH over here are not going to like each other. They're too close together. They're going to create this torsional strain, which makes an unstable molecule. So now we can go through a couple of more examples, and this is actually going to be, I'm going to ask you guys some questions, and hopefully you can pause the video and see if you can solve it for yourself. So let's start by going to butane. So let's do butane. So I want you to pause this video and see if you can draw out the staggered Newman projection for butane. All right, so for the staggered one, first we need to draw out our circles. So this is our back carbon, and let me get my bigger circle over here. This is going to be our front carbon over here. Let me move this down a little. So butane. Butane is going to have 4 carbons. So we have 4 carbons, so 1 carbon over here, carbon is on the back over here. So what we're going to have is a CH3 up over here. Then we're going to have hydrogen and hydrogen over here. And on the back, we're going to have our CH3, then H over here, and H. Now, one thing you'll notice with this Newman projection is that the CH3s, those methyl groups, are farthest away from each other. And this is really important to understand because, first off, we can both agree that methyl is much bigger than hydrogen. And since it's bigger, it's going to have a larger repulsive force if it's with another methyl right next to it. So we don't want that. We want to have the largest molecules farthest away from each other. So in this case with butane, CH3, those methyl groups, are the biggest ones. So we want to make sure they're as far away as possible so we don't have any torsional strain. And this is going to be butane's anti-conformation. So anti-conformation. And this is going to result in 0 kilojoules per mole of torsional strain because those methyl groups are as far away as they can be. So you can think of this as like Mean Girls. You know, there are 3 of them. They're called the plastics, and the plastics cause a lot of drama. So in order for, you know, the high school to not have as much drama, not have as much conflict, these plastics need to be as far away from each other as possible. And these H groups are just like normal high school students in the movie. Like, they don't cause much trouble. If anything, they just go to parties, this and that. But these methyl groups are the plastics, and you need to keep them as far away from each each other as possible, or else they're going to cause a lot of trauma or a lot of drama. And that drama is what we capture as the torsional strain. So you can think about it like that. If you have bigger molecules, you need to have them as far away as possible because they're going to cause a lot of drama, they're going to cause a lot of energy, and make the whole place unstable. So now I want you to pause this video and see if you can draw both the eclipse conformations for butane. So our first eclipse structure is going to be when we rotate our anti-conformation by 60 degrees. So this is what one of our eclipsed conformations is going to look like. And this is going to be 16 kilojoules per mole because there is some torsional strain over here with all those HCH3s, and this HH over here is going to have some steric strain. And our last eclipse conformation is actually going to be the one with the highest energy, and it's going to be this one over here. And the reason why this has the highest energy is because both of those methyl groups are as close together as possible, versus this one, they were really close to the hydrogens, so there wasn't as much torsional strain. But over here, with those methyls, they have the highest torsional strain, which results in the highest, least stable organic molecule form of butane. Now you'll notice in the middle, I forgot one conformation, and this is actually called the gauche conformation. I think it's pronounced that way, or gauche, whichever way you want to pronounce it. This conformation is going to result when we move this guy over here by 60 degrees. So we're only moving the back carbon. Remember, we can only move the back carbon when we're rotating our organic molecule. So when we rotate this 60 degrees, what's going to happen is we're going to have something like this. So our methyls are close together, but they're close in a 60-degree angle. So they're not as close as the eclipsed. And this is what the gauche conformation is. And this only results in 3.8 kilojoules per mole of steric strain. So I'm going to write over here of steric strain. And steric strain occurs when these atoms are forced closer than their atomic radii can allow them to, or it's basically when these bulky atoms are close together, and this creates steric strain. But steric strain is less in energy compared to torsional strain, because torsional strain has those bonds. But with steric strain, we're mostly talking about the atom and its atomic radii and how that can actually generate energy. So over here with steric strain, remember, we're focusing on our atoms. So this is, I'm going to write over here, this is when bulky is together. So bulky is together, but this is going to be in a 60-degree angle. So this is going to look like our staggered or our anti-conformation, but our methyl groups are close together. And over here, this is going to rotate 60 degrees to create that eclipsed conformation. And over here, we can rotate this by 60 degrees to create that most unstable eclipse conformation over here. Now, one thing to note is that you can only rotate the back carbon by 60 degrees. That's why we're going by 60 degrees throughout this whole Newman projection, because that is literally the only way you could move or rotate the molecules. And you could go around this whole pattern again, rotate by 60 degrees. You're gonna create the same thing, because with this butane over here, we're only gonna have 4 different conformations: our anti-conformation, eclipsed, the gauche, and the highest, most unstable eclipsed conformation. And one last thing to help you guys understand where we get this energy from and how different strains can increase energy. One of the things that could be helpful to know is that if we're looking at this eclipse conformation and we have hydrogens that are close together in this eclipse, this is going to create 4 kilojoules. Let me actually go to a lower font over here. So this is going to be 4 kilojoules per mole of torsional strain over here. So I'll just do this. And if you see a hydrogen and hydrogen that are in an eclipse conformation, this is going to create a torsional strain of 4 kilojoules per mole. And over here, if we have that same thing but with a methyl and a hydrogen, this is going to result in 6 kilojoules per mole. So 6, and same thing over here, I'll just do 6 over here. So 6 plus 6, 12, 12 plus 4 is 16, and that's where we got that 16 kilojoules per mole. Over here, it's actually the worst because we have 2 of those methyls together, and this is going to result in a torsional strain of 11 kilojoules per mole. There's also some steric strain in there as well. And over here, this is going to be 4, so 8 plus 11, 19. Now over here, since our hydrogens are in this gauche conformation, there's not going to be any energy. There's not going to be any torsional strain or any steric strain, but there is some steric strain between these 2 methyls. Since they're just so big, they're going to cause some drama, but not enough to where we have a unstable organic molecule. So this over here is just going to be 3.8 kilojoules per mole, which is where we got that 3.8. So hopefully this makes sense in that if we're looking at those eclipse conformations, we're pushing the atoms closer together, and they don't like that. We're pushing the bonds closer together, which creates torsional strain. And when we're looking at gauche conformation, we're pushing those atoms to the point where their atomic radius doesn't really like it, and they're going to push back, creating that energy. So hopefully this video made sense, talking about torsional strain, steric strain, eclipsed, staggered conformations, and hopefully you understand this and you're good with chemistry now. And as always, a Pomodoro day will make you a doctor someday. I'll see you guys in the next one.